So what we've got going on here is we have those trust problems that are coming due. Okay, we have a test a week from Monday too, so keep that in mind, okay? So, I should say this coming Monday is what I should say, okay? So, and that'll cover, and I'll get you that review sheet tomorrow. I don't have it for today. Got a little busy, but so that'll be a week from yesterday. So that'll be the 20th, I think. That review sheet's online too for those of you that are online. All right, so we've got some trusses here. And then, we have kind of this standard way of going through these. There are pages that are laid out for you to do this work on. It does take a little while to do it, so be aware of that. So the first one is 292. It's just a standard truss that looks like so. So there's a series of steps for working through these things. The first step is to find the reactions. And then I also do the trigonometry to find the angles. So I want the reactions and the angles when I first go through these, okay? So that would be the first thing that I would do. So I went ahead and worked through that. So I got the angles there at A and B. They're the same. They're 36.87 degrees. And then the angle at F is 56.31. And then I went ahead and I found the reactions. So that's the first thing that you would do on these things. This just kind of gets set up and good to go. Generally speaking, you do not want to try and just jump into these without having the reactions. So that one there is 21, and this one here is 54. Okay, and then we've got the angles there. So we got any questions on that bit? And what you're doing there is you're treating the truss as one whole object. So what I would do there, I would sum moments about A probably, set that equal to 0. I've got those unknown reactions at A and F. I also have an X reaction at F, but it will zero out because there's no applied X forces. So when I do that, I've got a clockwise 15 there. So 15 kilonewtons, 2 meter moment arm from A, clockwise gets me a negative. And then I've got the other force there at D. So that's 60 kilonewtons times 4 meters. And then 1 more meter out, which would be 5, I've got my unknown reaction at F. So that's RFY. So that'll get me RFY. And that'll be 54 kilonewtons. And then once I've got that, I just sum forces in the y and set that equal to 0. And I'll have my unknown RA minus the 15 minus the 60 plus the 54 that I just found. And that'll get me RA then, which is 21. Okay. So that's the basics for finding the reactions. So we good on that? Starting with the reactions. Now, once you've got that, you want to start at a joint that has at least a known force and only 2 unknowns. Okay, so that's the next bit. So the first thing you do is the setup work. You find the reactions on the truss as a whole. You find the angles for the members. Okay, then you want to start, usually at one end of the truss or the other. Look for a joint that has only 2 unknowns and has some sort of known force on it. Okay? And then once you do that, you can start to run in and go from joint to joint. All right? So I started at joint F. You could just as well start at joint A. So what I would like you to do on these, to get full credit and all that, is to draw a free body diagram of each joint that you work on. So I'll start on joint F, and I've got 54 coming up. Now I kind of go through a sequence in my mind to kind of figure out what's happening with this. I've got DF coming down like this. Now I know the 54 is up, so DF has to be down in compression. If DF is down in compression, what that means is that EF will have to pull to the left, because DF, if it goes down, also has to push to the right. So I go ahead and do that. So I just, often when I'm getting these free body diagrams together, I just reason through it a little bit. And that's 56.3 degrees, like so. All right. Now, once you've got that, the next thing to do is just to write up force equations for that joint. So what you're doing, this is called method of joints, is you're finding the force, finding the equilibrium equations, I guess you'd say, for each joint. So I'd go sum of Fy there and set that equal to 0. Now I'm starting with y because I've only got one y unknown, and that's FDF. So I'm going to get 54 up, and then minus the y component there, which would be the sine of the angle, times the unknown, which is FDF. And then once I've got that equation, I can find FDF. Now I started with that, with the y equation, so I can solve directly for FDF. If I had started with the x equation, I would have had two unknowns immediately, which just makes the calculations a little bit harder to do. So I just went ahead and started directly with the y equation, okay? And so that'll get me FDF. And when you work through that, that'll be 64.9 compression. It came out to be a positive 64.9 when I solved it. And I assumed it was pushing down on F, down and to the right. So my positive answer means my assumption was correct. It does push on the joint down to the right. Okay. And then once I've got that, I can go sum of Fx. Set that equal to 0. And what I'm going to have there is I'm going to have cosine 56.3 times FDF. And then to the left, I'll have FEF. So that'll get a negative. So then I can solve for FEF. And that will come out to be, whatever the heck it is, it's 36. And that'll be tension. It's pulling back to the left. So that's how I would start this. I'd start either at A or F, one place or the other, and then just go ahead and work my way through. Yeah, question?
If we guess that something's in compression, then we find out it's in tension. On our free body diagram, do you want us to change the direction we show it as?
No.
Okay.
Once you get one free body diagram, you're good. A negative answer, again, just means turn it around. And just remember, you work on to the next equation, though, you might need to remember, that does actually act in the direction. Do the one thing. But yeah, you don't need to redraw it. Okay. Other questions on that? Okay, we're good. Okay. Okay, so we got DF is 64.9 compression. So remember, if that pushes here, it also pushes there, and that came out to be 64.9. And then EF is in tension, so it's pulling on both joints, and that's 36.0. So once you've got that, you can go to the next joint. Now what I notice there, if I go up to D, I've got 3 unknowns, so that's too many for me to handle, so I'll probably go to E next. And that one will be pretty easy. Okay, so I've got my joint E, and that's pulling, that's tension, so that's 36 doing this. I would assume then that BE goes the other direction. And then I've got DE going up. So if I go sum of FX equals to 0, I'll get negative FBE plus 36. So FBE will be 36 tension. And then if I go sum of FY equals 0, all I'm going to get there is FDE. So FDE is equal to 0. Okay, so DE is what you'd call a zero force member. It has no force in it. Okay.
On a test, would we label that on the quadratic diagram, the 0? Biggest variable.
Depends what I'm asking you. If I specifically say label them with zeros, you know, obviously, you know, but unless I say specifically put a 0 on it, yeah, you really wouldn't have to. Just have to realize it's a 0. So that one's 0, and these are in tension here with a magnitude of 36. Okay. So the process is, once you get going on these, you just start working through and work your way from joint to joint. Keep in mind you can only handle 2 unknowns at a joint, and you need some sort of known force there to start out. Okay. Good with that so far? Maybe we'll look at one other joint here if you want. Okay. Okay, I'll probably go up to D next. So now I've got enough to solve joint D. I know that DE is 0. So I know this one's compression, and it's 64.9, 56.3 degrees. Now that DE is 0, so I could just as well leave it out, you know. I wouldn't even put it in there because it's 0. At the top, I've got 60 pushing down. So remember to pick up the applied forces, okay? Not just the forces in the members, but the applied forces. Given what I'm seeing here, so we good so far here? Doing all right? Well, at BD, you know, I don't know. Probably compression is probably pushing up, and that's 36.87. And then CD is, those top members are usually in compression as that thing kind of bows down. I mean, I don't know for sure, but that would be my assumption there for CD. But why don't we just put it in tension just to show what happens? So let's do this. Okay. So there it is. There's the free body diagram. All right, now I've got only one y unknown there, so I'll start with the sum of Fy equation. Set that equal to 0. And what do I got? I got that negative 60. I've got plus sine 56.3 times 64.9. And then I've got plus sine 36.87. And that'll be times BD. Okay. So minus is down and positive is up. And I just work through and get the trig components of the different forces. I go ahead and solve for FBD. It's 10 compression, so that comes out to be positive 10. And I go sum of fx and set that equal to 0. Okay. So I got minus FCD plus cosine 36.87 times 10, because that's to the right, and then minus cosine 56.3 times 64.9 to the left. Okay. So I'm just looking at all the forces that act in the x direction. And then I can find FCD. And as I have that drawn, that'll be negative 28.0. Now what I've done here is I've assumed that FCD pulls to the left. That's been my assumption there. So that's why I'm getting the negative, okay? Because it turns out it doesn't do that. So that's what the negative on my answer means. So all I have to do to correct that is just change the assumption on my answer. That's all I got to do. So I'll just write out that'll be 28.0, and instead of being tension, that'll be actually compression for CD. Okay. Everybody okay with that? All right. And that's the method of joints. I mean, that's how it's done. It's a process again. So, you know, that'll definitely be on the test, and so you want to get that one figured out, how to work through a truss like that. Okay. So the things to remember here are what? Find the reactions first, find the angles, and then start at a joint with only two unknowns and some sort of known force. And then start working your way through the truss with these joint equations, setting the joints equal, the forces on the joints equal to 0, and using trigonometry. Remember, the members are either in tension or compression. If they're in compression, as is that member there, DF, it's pushing on joint F, but it's also pushing on joint D. If it's in tension, as is EF, it's pulling on joint F, but also pulling on joint E. And then you just work your way through the truss. Questions there? Okay. You know, you keep working your way through that. Now, remember when you get to the end, just fill in the answer blanks there. And basically that's just an organizational thing. I can't be hunting around for this many answers all over everybody's paper. So I do want you to do these on the page that I gave you, 17A and B. If you want to do them on separate paper, just be sure you list your answers vertically in that same order so I can check them quickly. Okay. In the same order. Okay. So we're good on that? Okay. All right. So that's a pretty basic truss there to work through. There's also a cantilever truss, this one here. And that's another one, you know, for you to do. Find the reactions first on this thing. You're going to be able to work through this one, at least on the periphery, pretty quick. You do have that interior triangle, that BCE. That's maybe a little bit tricky. Not that bad. It's just you're going to have to do two equations and two unknowns with that, or you're going to have to use inclined axes. One or the other. You know, it's not, you know, I wouldn't say it's all that terrible or anything. It's just what you're going to have to do with that. The reason is for all those joints, you've got at least two members there at angles. And then, so they have both X and Y components. So that'll lead you to two equations and two unknowns, or inclined axes, as I was showing you, or something like that to work through it. So, you know, these you'll be able to get pretty easy, you know, these ones. What do we got? We've got this moment coming around, so the reactions are going to do that, aren't they? So you should be able to, you know, to get AC and AB pretty quickly. And the challenge would be on that interior triangle. We got any questions on that one?
On the formula sheet, you gave us law signs and law cosines. Are we ever going to use that, or can we always just use tension?
Yeah, I gave you the law signs, I think. Yeah, I never, in statics, I don't use it.
Okay,
Use
it's
it
not
in
going to show up on a test?
No,
Okay.
no. Other questions on this one? Doing all right with trusses generally? Okay. So once you get down there to joint E there, you know, you might have to set up an X and a Y equation and do some substitution. Or you might have to do inclined axes, you know, one or the other. So, you know, whatever way works for you is fine. I'll give you the answers on these so you can see how you're getting through them, okay? Okay, then we got some zero force members. So these are due as well. So what you do for these is you just take the page out of the book. This is page 18, and mark the zero force members with a 0. Okay. So, and that's really all I need you to do is just mark them. So remember what you're looking for. Unloaded corners with only 2 members, unloaded T's with only 3 members, and then there's also that special one with a 2-member corner with a collinear load applied. You'll have 1 0 in there also. So let's see what we got. Sum of fx is 0. That's going to be FBD, isn't it, if I look at this joint here? So that's a 0 right there. All right, and I bet if you go sum of fy equals 0, you're going to find that this one's 0 too, right? Any questions on that? Probably going to find a couple others in that one too, okay? So probably there's a couple other zero forces in that one. Any questions on that? Okay. Okay, on this one, sum of Fy equals 0. That's going to equal FCF, right? It's for joint C. So that'll get me that one's 0, FC, okay? Now, even though I've got an angle in here, doesn't make any difference. I can do the same argument and get FB as 0. Okay. Probably got at least one more in that truss too, okay? So the one before was unloaded corner. This is unloaded T here. So probably got another one in there. This one, we got a few in here. This is that funny one with the collinear load. You look down here and you go sum of Fy equals 0. You're going to get CF. So that's a 0. I think you got, another 2 or so in that one. Okay. So what's going on there, you're making the assumption that P3 is directly in line with EF. So EF absorbs that load P3 completely. So CF has no force in it at all. That's the assumption there.
Is P1 not pushing down on?
Okay, P1 is pushing down on B. You can't use that transmissibility of force idea on trusses because there's so many ways for forces to be picked up kind of through that spider web of members. So that P1 for sure is pushing on BC. You look at joint B, but I can't really say anything that's happening down at CF because I've also got that CE, that could pick up a vertical component too. So you just can't take a force and slide it down. You can't take P1 and put it right there. That's kind of breaking the rules. You can't do that.
You can assume that it doesn't go straight.
You can, I'm sorry?
I'm asking if you can assume that it doesn't go straight past BC.
You can assume that, yeah. I mean,
How do you know that it doesn't?
okay, how do I know it doesn't put pressure on CF? The reason I know it doesn't put pressure on CF is because I'm looking at joint F. And that's how you approach these zero force members. You look at one joint or the other. And when I do that, I don't look at joint C at all. All I'm looking at is joint F. And looking at joint F, I can see that FCF is 0 because the sum of Fy is 0 at joint F. Once I conclude that CF is 0, then I can go up to joint C and I say, well, it doesn't bear any Y force up there. If you can prove it on one joint, the thing's 0 and you're done. So you kind of have to focus on one joint at a time and kind of discipline how you look at things. Look at the joint, not the whole member. I know it's a little odd. You're looking at joint C and it sure looks like it would because it's right below. I understand what you're saying, but that's not how you do this. You just look at that first joint F. It's 0. I'm done. I don't even think about it after that. It's gone. Okay. Yeah.
You said there is pressure on joint F, but it's an X direction.
Yes, right.
So you'd still call it a 0 force member?
Well, CF is in the Y direction. So there's an X force on the Y joint, but so EF is not 0.
Right.
But a 0 force member, that's like CF is a member.
Oh, CF is a member.
Yeah.
Which is
A beam or a column or whatever, yeah. Yeah, so I think that's about terms that you use. A joint is where members come together. A member is like a long, thin piece of metal. Okay. Other questions? Yeah.
So CB wouldn't be 0 because it has P1.
Correct. Yeah, when I look at joint B, P1 is very likely taken up by BC. When I look at joint C, there's so much stuff going on there, I can't infer anything about CV. When I look at joint C, there's just too many things going on.
CD would also be a 0, but
Maybe.
it's otherwise D would be flying off the distance.
Hmm?
Wouldn't it have to be, because otherwise D would go flying off the distance.
Maybe. I want you guys to solve a few of these, so I don't want to start answering too many of these. Other questions? Yeah, I know, it is downstairs. It's funny, it might be coming in through the ventilation system or something. We're hearing it, I don't
I wonder
know.
what actually is that's making that
They're
noise.
drilling, I think. I think they're core drilling some of those posts, maybe. I'm not sure. So we good with this one? Other questions? Yes.
What about
AB?
Yeah. It's kind of like
Yeah, it is. But remember, those angles aren't always that significant because when you just do a sine or a cosine of an angle, you just get a numerical coefficient. It doesn't really enter into things. And what I mean by that is on this one, you know, BF is an unloaded T at joint B, just like CF is. The angle of BF doesn't make any difference. It's just a coefficient that gets thrown into it, but it's just a number, you know, it doesn't make any difference. So if they're at a little bit of an angle, it's not, or any kind of angle, it's not a big deal, you know. Don't let that hang out. So just write the equations. If you can prove it's 0 at one joint, it's 0. And, you know, kind of get on with your life after that. Don't, you know. Okay. What's that now? Oh, that's just a goofy looking truss, this one. So I'll just let you figure that one out. You know, it may not have any zero force members, I'll say that, so don't invent them. And just prove them out, you know. Write an equation for a joint. Just don't look at them and say, oh yeah, it looks like a 0. You know. Until you get competent enough to do that, just do a little equation at a joint. So, you know. This one has a number of them. All right, so I can do that joint C there. And I can go sum of Fy. So this is a good example of what I mean by that angle stuff. If I got an angle theta here, what I'm going to have is sum of Fy is 0, and that'll equal sine whatever theta is times FCB, right? So that sine of theta doesn't make any difference. It's just a numerical coefficient. So CB will be 0. That's about all there is to it, okay?
Well, last time you said that whatever, like the P1 down is doing isn't going to affect anything else besides like the thing that it's directly under.
Yeah, okay. I said you can't infer it. You can't use the principle of transmissibility. So P1 is going to have to work its way down to the supports, but, you know, and I know it's going to affect BE and EF, but other than that, I don't know too much. I mean,
Well, do you know that it's gonna affect BE?
well, actually, I don't really. I mean, right. Well, I don't know. I mean, again, you just have to look at a particular joint. I mean, I'm not going to look at joint E to figure out any of those, really, because it's just so crowded. There's just too much stuff going on there. I'll look at joint C and joint D, and I'll look at joint B, and I'll look at those other joints to figure out what's going on with those. See, I don't. Yeah.
But how can you tell if it's pushing or pulling it? Joint C.
Well, joint C, it doesn't really matter. I see, I'm just going I'm summing the forces in the y direction at joint C. And when I do that, I get that equation. I can have sine theta FCB. I could have negative sine theta of FCB. It wouldn't make any difference. It'd come out to be 0 either way. So I don't really care whether it's pushing or pulling. Okay. Either way, it's just zeroing out. Okay.
Because there aren't so many dimensions.
Yeah, right. There's just nothing else going on in the y direction at joint C. There's one thing, and it's BC. So BC is 0. If it isn't, C is going to start moving up or down. You know, just F equals ma. I mean, you got to have balanced forces in statics. Okay. All right. Now the one thing is on these things, once you find something is 0, remember to take it out of the truss. Okay. Once something is 0, it's gone. So once that's 0, I'm not going to deal with it anymore. And what I can do then, I can just pull it out of the truss, and I can come on up here and I can do x prime and y prime. And then I can look at that joint. Okay? And when I do that, what will I figure out about BD? That's 0, yeah. Okay? So that'll 0 out too, because I can go sum of Fy prime is equal to 0. And I don't know if that's got an angle or not. It doesn't really matter. It's just FBD. Maybe there is an angle in there. I'll throw an angle in there. I'll call it phi. So I can infer then that FBD is 0 now, okay? When I do that at joint B. So remember, once something's 0, you can pull it out. You know, and kind of keep going through the truss after that. Once you've found something 0, it's 0. So, you know, you can pull it out of the truss then when you analyze. Got questions on that? Yes.
Well, key to it, is it pushing like it's not touching you, it's just kind of like
That's on joint B.
so it's pushing on the joint.
Pushing it down. It's not like a weight hanging from it. Okay. So other questions on this stuff? Yeah.
So, like, would you say that the surface is pushing on
The support is, yeah. I mean, you know, there's a reaction there. So, yes. Yeah, I mean, when you have these supports, I would assume there's reactions there in the y direction. I think that's a fair assumption. So that would be pushing up on AB. Yeah.
So some forces of those would be 0.
Correct. Yeah, AB is not a 0, nor is FH. Okay. Doing all right with that? Okay. Okay. Now, you know, again, I'll warn you again that those things take a little while, so give yourself some time on that. And why don't we just start in on this stuff a little bit, and then we'll finish this up Wednesday, tomorrow. Okay, there's one other method for working through trusses. It's a little faster method, but you use it to go inside a truss and find the force in 2 or 3 members. So it's called method of sections. Page 520. So the idea here is you can find specific members with this method of sections. What you would do is you first find the reactions. So they become known forces. And then if the entire truss is in equilibrium, any part of it is in equilibrium. So what you could do, for instance, with this truss, once you find the reactions, you could go inside of it and find the forces in FD and EF and EH by making a cut through them. So the first thing you got to do is find the reactions, which I went ahead and did there, down here. So here I'm just finding the reactions on the truss as a whole. So what I got RBY is 6,400, and RK over there on the right is 7,600. So that's 6,400, and this is 7,600. Okay, so I just go ahead and find those reactions. Now, once I've got those, they're known, okay? So those are now known forces. And what I could do now is I could cut through the truss. It's like I'm taking a saw and cutting through it, and I can make any cut I want as long as I don't cut through a joint. I can make any cut I'm interested in. And then I know that if that whole truss is in equilibrium, what I cut free is also in equilibrium. So if I'm interested in finding the forces in FD, EF, and EH, I could make an imaginary cut through the truss right there. And that ADBE rectangle is in equilibrium. Then I can just analyze how the members I've cut through are pushing and pulling on that ABED rectangle. So what I would do then is I would generate a free body diagram that looks like this. I've got that rectangle that I've shaded in a little bit there. That's in equilibrium now. I've got the reaction that I found acting on B. I've got the 6,000 up there on D. And then these members here that I've made that imaginary cut through are now forces acting on that rectangle. They're pulling or pushing on it. So I could solve for these just using basic equilibrium. Okay. So this is called the method of sections. And you can use this to go inside of a truss and find the forces in some of the members quickly when you need to just find 1 or 2 of them. It's handy for that. Okay. So what you do, you find the reactions like you do with a truss. Then you determine what you want to find, which members you're interested in. You cut through them. And when you cut through them, they become independent forces that you can solve for. The stuff you don't cut through is in equilibrium. The members you do cut through are forces acting on that object you did not cut through. So I've got that little rectangle there, ABED, it's in equilibrium. The 3 members I found are pulling or pushing on it, and I can solve for those forces. Okay.
And like before, those are assumptions?
Yes. Yeah, they're assumptions. I've got them all in tension. They're not all in tension, yeah. So I'll get some negative answers. Again, no big deal. Negative answer, turn it around. No big deal. I've got them all in tension because Dr. Spencer T. Brinkerhoff used to do it that way, and never did anything contrary to what he did. It was just a recipe for trouble. So I still do that. So, but you don't have to. I just always show them intention. That's just the assumption I made because I was taught that way, so that's how I do it, but you wouldn't have to. Okay. So I just thought I'd mention that's what we're gonna do tomorrow, and then we'll get into that a bit tomorrow. Okay. So there you go.